All right, thank you very much for the introduction. Thank you for coming to my talk. Thanks to the organizers for this amazing conference. Thanks for having me here. So it's really a pleasure to share some of the recent results that we're hoping to be able to write up and put on the archive by this conference. And we had a very good intention. I promise you that. We didn't manage it quite. So hopefully it'll come out on the archive real soon. And this is some amazing. This is some work with this amazing colleague, Sumit. So the usual picture, one of the pictures that we might have about thermalization in many-body systems is if we imagine we might have some complex many-body system that starts in some initial state. There's some Hamiltonian that the system evolves according to. We might even know exactly what the state is, what the Hamiltonian is, and what the time is for which this Hamiltonian has been evolving. It's going to evolve to some state, but the point is, after a while, if we come and do some measurements, and the measurements are fairly, they're local observables, they're things that we can measure, we access a certain very restricted set of measurements usually, and these typically, according to these observables, for all practical purposes, this state kind of, even though it's some complex pure state, we can usually replace it by some mixed state, which we call the thermal state. That reproduces all of the statistics that we're interested in from this original big complex state. Now the question is, well, we had this kind of complex state psi. We want to replace it by some mixed state, so what state should we pick? Right, well, one of the approaches that we can use is to say, well, let's say there are some macroscopic or there are some physical observables that we have access to, and we know that their average over the state is some set of fixed values. And there's a very nice and elegant principle that allows us to single out what state should be this kind of mixed thermal state, and that's Jane's maximum entropy principle. So Jane's principle tells us that the state that we should use to maximize the state that we should use to replace this pure state is a state that maximizes the entropy subject to all of the expectation values matching the corresponding values on the state. So we're familiar with the result that the state we get is the familiar thermal state, which has this Gibbsian form and partition function. Right. So this thermal state, this Gibbs form thermal state is very common, not only in physics, even though I motivate it through statistical mechanics and thermodynamics and many body systems. We encounter it in many areas throughout algorithms and information theory. It represents kind of, in general, the least informative state that's compatible with some type of prior knowledge or some prior information. So, it's natural that you find it throughout classical and quantum algorithms, for instance, if you do some type of mirror descent optimization, algorithms like matrix multiplicative weights, quantum shadow tomography, some algorithms for solving SDPs, some quantum algorithms. Well, they're based on this type of, this state is somehow going to appear out of it. And one algorithm I like to single out because it's also related to what we're going to do later is this learning algorithm for quantum states that's been explored in these references among people in the audience as well. And this idea is that you update your knowledge of your state according to new measurements that come in, and these measurements, and the way we update the state is essentially keeping track of the maximum entropy state that's compatible with the data that has been observed up to this point. Now, this Gibbs thermal state, there are actually many ways of characterizing it, of identifying it. So we can identify it, as we just said, through Jane's maximum entropy principle. We can use, there's another textbook approach to say what is the thermal state, and that is to look at a microcanonical ensemble over, say, many copies of a system or the system in a large bath, and then to look at the reduced state of that on a single system. And there are other approaches, like what happens if we have something like, again, a microcanonical ensemble, but we don't take some type of mixed state over this subspace. We really pick kind of almost any state in the subspace that gives rise to things like canonical typicality. We can think about passivity and say, well, what is the state from which we cannot extract any work, even if given multiple copies? We can frame this in the context of the resource theory of thermodynamics as well, and there it turns out that the thermal state is kind of the unique state that you can allow for free without trivializing your theory. And of course, one of our starting points was, there's this dynamical equilibrium picture, which is, well, the thermal state is the state that you're going to tend to, essentially, in some specific sense, when you evolve a sufficiently complex, sufficiently ergodic or thermalizing system in time. Now the idea I wanted to present today is, what if we replicate this type of reasoning and this approach to understanding what mixed state to replace a pure state by? What if we replicated that idea not to the state, but to the actual entire dynamics, and think of that as some big channel? Think of this as some big unitary that maps input states to output states, and then somehow let's imagine: is there a way of replacing this unitary dynamics by something like some big channel, some noisy channel that is not at all going to reproduce U of t exactly at the microscopic level, but maybe for the things that we care about, for kind of maybe some set of input states and output measurements, it's going to reproduce all of the interesting things that we know, and it's going to be some thermal version for the evolution, in the same way that we're thinking of a thermal state for the state of the system. So we might want to ask, well, is there a sense in which we can say, well, this thing, is there a sense in which we can formulate a maximum entropy principle for channels? So we'd like to maximize something that we might want to call the entropy of a channel, and then we want to, make that subject to accessible to some type of expectation values that we have access to. But the question really is, well, what is this function, this entropy of a channel that we want to optimize, right? Now, thankfully, there has been in the literature a convincing definition of what the entropy of a quantum channel is. And let me give you this definition right here. We can imagine that the entropy of a channel that has high entropy should be a channel that kind of is guaranteed to always produce an output state that has high entropy, regardless of the input state that we feed into it. So if I take any input state, I feed, and maybe there's even a reference system I'm allowed to keep along, right? So I feed any input state to my channel, I look at the output, and I want the entropy of the output to be high for all input states, even conditioned on some side reference system that we've kept along. There's another definition which is absolutely equivalent. So if we kind of remember that we're all information theorists deep somewhere in us, and how do you define an entropy? Well, one of the kind of information theoretic flavors of defining an entropy is starting from a relative entropy. And so if you start from a relative entropy, there's a natural way of defining that for channels, and it's to take the state relative entropy and of the outputs of the channels, including the reference, and then optimizing over all input states. So you can think of this as a natural kind of relative entropy version of the way you define the diamond norm, for instance, of channels. And so we get another expression for the channel entropy. And if you stare at these for a moment, you can see that they're equivalent, because you can express the conditional entropy as a relative entropy, and kind of this minimization we have here turns into this maximization we have on this other side through this minus sign. All right, so we're armed with this entropy of a channel, so we can formulate something like a maximum channel entropy principle. So we want to maximize the entropy of this channel over all CPTP maps, over all channels, and we have these constraints. So previously I suggested maybe a constraint might be input state or an output measurement fixed to some value. Well, in general, it's just let's just pick a set of linear constraints on the channel, which I can always express as a bunch of linear constraints on the Choi matrix of the channel. The Choi matrix, which I'm writing like this as n subscript br, that's the Choi matrix of the channel n a to b. All right, so this is the problem we want to focus on. Some quick observations about this problem is it's not obvious, but so remember, in this entropy of a channel we have this minimization, and in general when we have max min of something, we have to be careful about the order in which we do this. But here it turns out that the function that we're optimizing inside this conditional entropy is kind of sufficiently well behaved that it's convex and concave in the right variables, that we can interchange the min and the max. So it's kind of a friendly type of optimization in this sense, and we can use a lot of tools from convex optimization, such as computing Lagrange dual problems or using strong duality to help us analyze this optimization problem. Right, and then again, I've said this already, that we can impose really arbitrary linear constraints on this channel. These CJs could encode anything you want. It could be anything from, for all input states, I need to have a certain output expectation value, to, it can be a fidelity to some channel, or you want a proximity to the identity channel, you can just take the overlap with the maximally entangled state between B and R. So this is really a general set of linear constraints on the channel. All right, so the first result that I wanted to show to you today is that we have a structure, a theorem that tells you what the structure of the optimal channel in this problem is. And I'm straight away going to caveat this, that there's a lot of fine print that I'm not showing you here. So like this is kind of generally the picture that you could have in mind. It's essentially, think of this as a generalization of the state Gibbs state, which I'm going to write in this form here. So imagine, if I write my thermal state as, if we're in general, if I have more than just a Hamiltonian but several charges, I'm going to get like a temperature or a chemical potential for each of these charges, and then I'm going to have the partition function, which I chose to wrote inside the exponential as some type of free energy, some generalized free energy, and or log partition function, or whatever you want to call it. And then these terms that you're going to find up there, they really mirror this expression here. But now you have these kind of extra phi r minus 1/2. And this phi r is kind of implicitly given as the state that optimizes this channel entropy. Right? So I'll come back to that a bit later as well. So this is kind of the general structure, the way you can think about the optimal channel that optimizes this maximum channel entropy thermal channel. So we can straight away start computing some examples. Well, if we don't impose any constraints at all, well, it's kind of intuitive. The channel we get is the completely depolarizing channel that erases its input and prepares a maximally mixed state. That's what you'd expect, and that's what you find. You can impose things like strict energy conservation. That's a set of linear constraints. And so what I mean by that is the channel must, if a state lives within a energy subspace, then the channel has to output a state within that same energy subspace. And that's a set of linear constraints we can impose on the channel. And there we find that the corresponding thermal channel is the channel that is completely depolarizing within each of these energy subspaces. Something a little more interesting is if you demand average energy conservation. So if I require that the trace of n of rho Hamiltonian output is equal to the trace of rho Hamiltonian on the input, that's also a set of linear constraints that I can impose for all input states rho. In that case, what I find is a channel that measures the input energy and prepares the Gibbs states associated with that energy that was just measured. That's an interesting example of a channel that actually preserves some information about the input state. It's no longer something that just destroys its input and prepares something at the output. It's really a state that preserves some memory of the input state. But it's still thermalizing because it prepares Gibbs states. And then you can do some kind of sanity checks. You recover the state Ks if you kind of constrain only the output. You can look at what happens if your channel is classical, if it's Pauli covariant, if your constraints are Pauli covariant, and things like that. So you can think of this as a kind of a general program of going from the thermal state. You're taking the different ways of thinking how should we think of the thermal state and seeing how they extend to quantum channels. So we just discussed the maximum entropy principle, and the next thing, and we can ask, of course, what about the other approaches? Can we extend those to quantum channels? And the one I want to focus now on is this microcanonical approach, and this is the one that is going to have this most beyond IID, or actually pretty IID, somewhat beyond, in this type of approach and techniques. So let's focus on that. How do we construct a microcanonical state for thermal states? First, let's look at the state case just to remember how it works. If I have let's say a single, or if I have multiple charges, physical quantities that commute, and I want to define a microcanonical subspace associated with these charges being in a certain definite value plus minus delta, well, I'll just take the simultaneous eigenspace of all of these charges with those values that I want to constrain, right? So I'm just going to take all the states that are simultaneous eigenstates of all of these charges with the corresponding eigenvalues over, now I'm going to look at these, of course, over, I forgot to say, over n copies of my system. So these are states that have very sharp statistics according to all of these charges. The problem, of course, is if these guys do not commute, if these charges do not commute, I cannot construct simply my microcanonical subspace in this way. I have to do something a little more subtle. I have to think about an approximate microcanonical subspace. And this is something that was explored in these works here some time ago. So what we do in this case is we say, well, maybe we won't be able to look at a subspace which contains really states that are simultaneous eigenspaces of my charges, but maybe they're kind of approximate eigenstates in a suitable sense. And the way we can formalize this is by saying that I want the state to have high overlap in the subspace, kind of if and only if it has sharp statistics with respect to all of my charges around the charge values that we want to set. So if I have high overlap, then it has sharp statistics, and vice versa. If I have sharp statistics, then I'm going to have high overlap. The reason I don't have a double arrow in both ways here is that I've, of course, not written out all of the epsilons and deltas, and then the epsilons and deltas might change depending on the direction you're going in. So that's the way we could do this for quantum states. Now, how are we going to do this for channels? The obvious candidate, naive candidate you'd write out first would be, well, let's try to impose some sharp statistics for this channel, for the Choi matrix, essentially. But then you realize, okay, how do you do that for a Choi matrix? A Choi matrix is not normalized. Kind of a Choi matrix is a representation of the channel where you have not decided what the input state is yet. So if we want to talk about statistics, you somehow need a well-behaved probability distribution, not something where that's not yet a probability distribution. So you could say, well, let's just normalize it. But that really means that you're looking at the maximally mixed input, or like a maximally entangled input if you think of the reference system. And you're looking at the action of the channel only on that input state. On, let's say, n copies of my system, well, the way we could do it, we figured out, was to say, well, let's imagine an observable where I actually kind of I kind of sandwich my constraint operator by this sigma r minus 1/2. If I know what my input state is, then I would kind of conjugate this by this sigma reference minus 1/2 on both sides. And if I do that, well, then this observable kind of, if I apply this on a channel with some given input state, then these sigmas are going to cancel out in the right way as long as sigma is full rank to give me really the thing that I wanted to measure in the first place, right? This is the thing that we want to measure. Right, so, and now this is something that we can impose for all input states, right? We could say, now for all sigma, we want something like we want some operator that's going to be this approximate microcanonical kind of channel operator. We want this to, we want that if a channel satisfies, if this operator captures the output of a channel on any sigma, including a reference, if it does capture this thing for all sigma, then we want this to be kind of equivalent to this output of E on any input state sigma to have sharp statistics with respect to this observable we just defined for that sigma that's at the input state, right? So if I prepare sigma and I measure the constraint operator tailored to this input state sigma, I want sharp statistics, and I want that for all input states. And I want this both ways. So there's kind of a subtlety here, which is kind of, if I have some low rank, if I have like some very small eigenvalues with sigma, this will not work because my observable norm is going to blow up, and that's a bad idea. So we're going to have to do things like restrict the, make sure that sigma is always full rank and has a manageable lowest eigenvalue and things like that. So, but I'm going to hide most of these details moving forward. So the first thing we can prove is that we have some type of operator that we call kind of something that's a POVM effect that kind of selects channels based on whether they have sharp statistics on the constraints. We can define something like a microcanonical channel, kind of mirroring a similar definition for states. The microcanonical state is the most entropic state within the microcanonical subspace. Well, let's do the same thing. Well, let's take a microcanonical channel as being the most entropic within the channels that are captured by this operator. And then we can show that if you look at kind of what happens, if we kind of feed in, if we look at what happens on a single copy of something that this microcanonical channel acts on with this phi that we came out of this optimization of the channel entropy, we find the same type of operator that you'd find if you had maximized the entropy of the channel for a single site as we did before. So in this kind of, in this particular sense, this microcanonical channel somehow leads to the thermal channel that we found from the maximum entropy principle. All right, now I gave you a definition of what this approximate microcanonical channel operator is, but I didn't tell you how to construct it. So now in the remaining few minutes, I'm going to try to give you an idea of how to do that and how to prove that it's actually it has the desired properties. So this is the theorem I'd like to prove, to try to sketch at least right now, because I won't be able to prove it, obviously. So there exists, how do we construct an operator like this? So the sketch of how to construct it is going to be something like this. So if we come back to the condition that we had, right? We had this condition here. Essentially, we want this thing is always going to be applied onto some channel acting on some sigma tensor n, right? So if we think about how to, if we think of a protocol that acts on this object, so we start with this object here. We have this initial state is just a channel acting on the sigma tensor n. And the first thing we're going to do is we're going to sacrifice a fraction of our copies just to estimate what the input is. So we're going to come up with some estimate. We're going to do some pretty good measurements, some suitable measurement just to get an estimate of what this sigma input state is. And then on the remaining copies, we're going to measure the corresponding this kind of sigma tailored observable for randomly chosen, on each copy we're going to choose at random which of the constraints we want to test, and we're going to measure all of these guys on all of the remaining copies. And then we're going to gather all of these statistics, process them, and come up with estimates of the values of these constraints over the data that we took. And we're going to see if they're all close enough to our satisfaction to the true statistics that we really wanted. Or in that case, we're going to accept, we're going to output accept. That's going to be the effect that corresponds to P. And we're going to reject otherwise, and that's going to be kind of the effect that corresponds to 1 minus P, or P orthogonal, the complementary effect. So the first thing that we can show is a simple kind of lemma that says that P is able to discriminate IID channels based on their expectation values of the constraints. So if I have a channel that has constrained expectation values that are closer, closer than some kind of tolerance A, then I'm going to have, did I mess this up? I might have messed this up. If I'm close to the constraints, then I should be captured by the channel. I think I got it the wrong way around. It's like P orthogonal is very low. And then on the other hand, if there's a value of the constraint for which my channel is far from the constraint value, well then it's going to be not captured by this projector at all. So it's going to be captured by the opposite. Yeah, I interchanged these two, P and P orthogonal. Right, so, and this is something that you can prove by using Höfting bounds and things like that. So at this point, we're kind of almost there. We're like if we were only looking at IID states, this kind of by using standard Höfting techniques, we'd be able to say that, well, states IID channels that are captured by this projector are in some sense also those for which also kind of these channels for which if I measure these constraint operators, then they would concentrate. So we're almost there, but we only have the result for IID channels. What we really do is we want to have this kind of equivalence for any channel E. And since kind of everything we're doing here is permutation invariant, I didn't tell you before, but kind of this protocol, we have to do it we have to symmetrize it in a way that's permutation invariant. It suffices to test this for a permutation invariant state. Now, of course, when I mention IID but we want permutation invariant, everyone in this room thought, oh, post-selection theorem, right? Or some type of Definetti thing. And that's exactly what we're going to do. Except, and so, to remind ourselves, if we have a permutation invariant state, then there's a post-selection technique that tells us that this thing is upper bounded by some convex combination of IID states. And there are versions of this Definetti theorem that kind of include this additional factor that's a bit tighter and that tell you kind of which IID states contribute the most in this decomposition. So we come up with a similar decomposition for channels that kind of generalize a bunch of existing ones. So we're going to use that to go from the state from the IID to the general case. So I'm going to kind of click through the proof here because I'm running out of time. But the idea is like we want to assume that kind of we have this, but we want to show this. So what we're going to do is we're going to apply this post-selection technique. We're going to get like two terms, one including this fidelity, the other one this IID term. We're going to use Höfting bounds and data processing inequalities and kind of our assumption to kind of take care of each of these terms in the right way to show that this bound that we wanted to show goes down. And this is the type of techniques. I'm kind of mostly showing you this at this point so you get a picture of what type of techniques come into this proof. Then we want to show also the other direction, but that's also very similar. So, in kind of, if we zoom out just a little bit out of these technical slides, what we had was we have this equivalence that we wanted to show that if you're captured by this projector, then you're also sharp in statistics with respect to this channel. That was the definition of this approximate microcanonical channel operator. We showed that there was a construction for this type of operator with a bunch of parameters, error parameters that I didn't show you, and that there's kind of under some fine print, this gives us again the same type of channel, maximum entropy channel that we had in the first part of the talk. So there are a few things that I kind of really glossed over at this point. It's these objects that came into this maximum entropy channel, these mu's, these f's, they're implicitly given by the constraints, so they might still be hard to calculate. And that's already the case for thermal states, right? So it's not going to get any easier with thermal channels, right? So it might still be hard to come up with actually what these optimal values are. We have kind of some results on what the optimal phi is for the channel constraints. Everything becomes more complicated if it happens that this guy is rank deficient, so there are some caveats around there I just want to mention. I also wanted to mention that in general, this optimization can in principle, it's convex. There are some tools out there. We're kind of working out what's the best way to do this optimization numerically, but basically there are a bunch of results here that are really helpful for that. So yeah, I mean, the thermal state, we find it everywhere in physics and information theory, so that might be an indication that the thermal channel might be something that's also useful for all these different tasks that we want to generalize from states to channels. It's something where I think we want to think of as some type of, as a tool to model anytime we have some type of dynamics that we want to describe as somehow thermalizing, but somehow keep some type of memory of the input. So it might be some situations where you have obstacles to thermalization in some way or another. For this crowd specifically, I thought like the microcanonical approach brings some combination of techniques that might be familiar to this type of idea and this crowd, and it closes in tightly with ideas of typicality and how to define typicality for quantum channels. And one thing I didn't have time to go over, which we have some very preliminary results on a learning algorithm for quantum channels that kind of is based on the corresponding idea for corresponding learning algorithm for quantum states. So we're still kind of trying to come up with a good proof principle at that point. So, I showed you this slide before with all of the different ways of characterizing the thermal state. And the remaining ones, they're kind of still open. So I think these are a few great open questions. And I'm going to stop here and thank for your attention and thank again my collaborator for this amazing project.
Thank you very much. We have time for one quick question, maybe. Yes, Felix?
Hey, Philippe. I have a question on slide 13. So you said that there's this problem that you want to handle arbitrary input states. Do you get the same result when you just use the Joy isomorphism? Because you're looking at a trace, and you can just put the,
I don't think you do. I mean, it's like the point. Well, I mean, I don't think you do, because like you need to, or maybe I'm I'm missing something, but like here, the point is you really want to test the channel not only on what it does on the maximally mixed state, but also on any other input state. So it was not at all obvious. It's not at all obvious. Like in a certain sense, I could tweak my channel to make it do something completely different on another IID state, and that's something that I wouldn't necessarily notice just by applying the constraint on the choice state. But I might be missing something.
You do recover all output states by like partial tracing against the input state, right, with the choice state. So, and you have a trace, so you could put all of this under the trace, and then maybe...
But the question is the normalization. You get an exponentially small factor because of the normalization. And that's kind of what messes you up in this case.
I mean, you can use this with the unnormalized state, too. Maybe let's talk offline about this.
But I'd be interested if you have so I wasn't clear how to do it with the unnormalized state, because then, your probability isn't 1. It's going to be kind of d squared. Like, maybe so if you have an idea of how to do that, I'd be really interested. Yeah.
I'm sure that there are more questions, but let's, I think you have to intercept Philippe in the upcoming days, so let's thank him again.
Thanks.